On a World War II battlefield, what happens when the power goes out? Absolutely nothing. Because it was never on in the first place. Like, long before microchips and satellites, before the digital world that defines modern warfare, soldiers relied on something that couldn't be short circuited or jammed: pure mechanical genius. While we rightly remember the thunder of tanks and the roar of fighter planes, many of the most critical battlefield tools were forgotten marvels of engineering. These were gadgets and systems that needed no plug, no battery, and no fragile electronics. They ran on springs, on pressure, on chemistry, and on the simple, elegant laws of physics. They were the unsung heroes of a world at war, proving that real power doesn't always come from a socket. Today, we're uncovering 12 forgotten technologies that prove you don't need a plug to be powerful. Number 1, before radar, listening to the skies. Along the British coastlines, before radar existed, before electronic systems transformed warfare, something remarkable emerged. They built acoustic mirrors, large concrete structures, sometimes 45 meters in diameter, designed to listen to the sky. Parabolic reflectors focused sound waves from aircraft engines onto microphones placed at their focal point. No electricity, no active components, just the physics of sound reflection. The same principle you encounter in a museum's whispering gallery. Locals still call the ones at Dungay in Kent and Hythe the listening ears. Microphones placed at the focus of these mirrors could detect aircraft sound at distances far greater than what any observer could see from the English Channel, and operators would listen through earpieces or stethoscopes as sound waves concentrated naturally through the mirror's geometry. Here's where it gets complicated. They almost never worked when it mattered. Aircraft speeds increased in the 1930s, meaning by the time an acoustic mirror detected a plane, it was already too close for meaningful defensive response, and the technology became obsolete almost as soon as it was deployed. But here's the thing that actually mattered. The acoustic mirror program, led by Dr. William Sansom Tucker, created something that survived the technology itself. The methodology for linking multiple detection stations to pinpoint an enemy's position in the sky was passed directly to the radar team, and it contributed significantly to Britain's radar success in World War II. A technology that failed in its primary purpose ended up making its successor possible. Sometimes the real innovation isn't what worked. It's what you learned by building it. Number 2, the mechanical computer that aimed artillery. Now something genuinely changed naval warfare. The Mark I fire control computer, developed by Hannibal C. Ford and William Newell. Weighing over 3,000 pounds, it sat deep inside warship hulls in a watertight compartment called the plotting room, and it was an electromechanical analog computer where the calculating mechanism itself was purely mechanical. A team of sailors stood around this 4-foot-tall machine, feeding it information: the target's range and bearing, the ship's speed through water, wind speed and direction, even the average muzzle velocity of the guns, based on propellant temperature and the number of rounds already fired that day. The Mark I then performed continuous mathematical calculations using 4 component integrators, devices that worked like ball-type computer mice rotating a ball to solve geometric equations. The computer automatically calculated lead angles to the future target position, adding corrections for gravity, relative wind, the spinning motion of the projectile, and something called parallax, because the guns were displaced along the ship's length. All of this happened mechanically through gears and rotating discs and cam mechanisms that physically performed the mathematics. Output went to the gun mounts through synchro motors that actuated hydraulic servos to aim the guns with remarkable precision. Ship-to-ship and ship-to-shore gunfire accuracy improved significantly, but the Mark I proved most valuable in anti-aircraft warfare until jet aircraft arrived and pushed speeds so high that mechanical systems couldn't react fast enough. Think about this for a moment. A 3,000-pound mechanical computer requiring no central processing unit, no digital logic, no transistors. It calculated firing solutions faster than humans could calculate them manually, and it kept doing it reliably for decades. Battleships equipped with the Mark I had up to 4 of these computers working simultaneously. Destroyers had one, and this system remained in service until 1991. Number 3, the most expensive bomb site in history. Carl Norden was a Dutch-Swiss engineer who immigrated to America in 1904 and started working on bomb sites in the 1920s. And the project nearly broke him. His early prototypes failed catastrophically. From only 3,000 feet altitude, his 1924 design showed a circular error probable of 110 feet, meaning half his bombs landed within that distance of the target. And that was worse than existing systems. Bombardiers hated it because it was too complicated to use. Obsession drove Norden forward. Year after year, he refined the design, and by 1928, he'd improved the accuracy to 2% of altitude. By 1931, when the Mark 15 version arrived for testing, the accuracy had improved dramatically. From 4,000 feet altitude, it achieved an 11-meter circular error probable, and even at higher altitudes, it delivered 23 meters. The Mark 15, later called the M series by the Army Air Force, combined a mechanical analog computer with optical sighting equipment and a gyroscopic stabilization platform. The bombardier would locate the target in the sighting telescope, then make fine adjustments using 2 control wheels throughout the bomb run. Inside the bomb sight, a wheel and disc calculator continuously recalculated the bomb's impact point based on changing flight conditions. All mechanical. All based on physical gears, cams, and rotating discs, performing mathematics. What nobody expected was the cost. The total development and production budget reached $1.1 billion. That's 2/3 of the Manhattan Project's budget. By war's end, 72,000 Norden bomb sights had been produced at $8,800 each. And here's the irony. That makes this technology so interesting. In actual combat, the Norden did not achieve its expected precision. The average circular error probable in 1943 was 1,200 feet, significantly worse than pre-war testing suggested. The difference between laboratory conditions and actual combat, between stable platforms and turbulent air, between theory and reality, turned out to be enormous. But the reputation endured, and that matters, because the mechanical computer inside that bomb site performed calculations in real time, continuously, without any electronic components. It did this so effectively that 72,000 of them were produced and deployed. That's the scale of mechanical engineering achievement. Number 4, the hand-cranked calculator designed in a concentration camp. Kurt Hertzstark was an Austrian engineer who managed his family's precision instruments company in Vienna, and when Nazi Germany annexed Austria, he fell under the Nuremberg laws, classified as a Mischling, or mixed blood person, because he had a Jewish father and an Austrian mother, a precarious legal status, a dangerous existence. The Nazis imprisoned him and sent him to Buchenwald concentration camp. While imprisoned, he was assigned to war equipment production for the Nazi state, and during that imprisonment, in that camp, he refined a hand-cranked mechanical calculator he had begun designing before the war. The curta was a cylinder about 4 inches tall, entirely mechanical, containing no electrical components whatsoever. You cranked it, used mechanical digit wheels and sliders to input numbers, and it performed addition, subtraction, multiplication, and division through pure mechanical motion. The innovation was significant because it used a modified Oedner mechanism, a mechanical system elegant in its simplicity and effectiveness. Kurt Hertzstark survived the camp. After the war, the Curte entered production, and for 2 decades, it remained the best portable calculator available until electronic calculators displaced it in the 1970s. Here's what's remarkable. Thousands of original curtas remain in working order today, and they're highly sought by collectors who recognize them as performing calculations just as smoothly now as they did 70 years ago. The story of the curta is the story of human ingenuity persisting even in circumstances of extreme duress. A mechanical calculator designed in a concentration camp, a device created under the worst imaginable conditions that outlasted most of the electrical technologies developed in comfort. Number 5. Submarine periscopes. Simple optics, profound impact. When you think of submarine periscopes, you probably imagine them as high-tech instruments, but they're not. Submarine periscopes are optical engineering achievements built from centuries-old principles and requiring no electricity whatsoever. Fundamentally, a periscope is 2 telescopes pointed into each other. Light enters the objective lens at the top, travels down a tube, gets reflected 90 degrees by a prism, travels horizontally, gets reflected another 90 degrees by a second prism, and finally reaches the eyepiece, where the observer looks. Magnification depends on the relationship between the objective and eyepiece telescopes. Focus adjusts manually through helical gears, and crosshairs provide mechanical aiming marks. That's it. That's the entire technology. Lenses, mirrors, prisms, and mechanical gears with no electricity required. The type to read daylight attack periscope was introduced into American submarine fleets in 1942 and found widespread use and acceptance throughout the remainder of World War II and for decades afterward. Search periscopes and night periscopes had larger heads to gather more light in reduced visibility conditions, while attack periscopes were slimmer, about 1¼ inches in diameter, to minimize visibility. The elegance of the mechanical periscope lies in its simplicity, because it required no active power, could be manufactured with pre-war precision machinery, operated reliably for decades, and gave submarine crews the ability to observe surface targets while maintaining submerged protection. That's a profound operational advantage derived from basic optics and mechanical precision. Number 6. Firing solutions at sea. Mechanical plotting. On warships, officers needed to calculate firing solutions for their guns, which required precise positioning of the target, understanding the ship's motion, calculating range and bearing, and predicting the target's future position. These calculations happened on mechanical plotting tables, rotating brass arms with protractors, transparent perspex rulers, and geared mechanisms for precise rotation. Sailors would plot the target's position by marking bearing lines from observation posts, then rotating mechanical arms to their correct bearings. Where these mechanical arms intersected, that's where the target actually was, and the entire calculation got performed through mechanical geometry, through the physical arrangement of arms and the intersection of lines. For coastal artillery batteries, Similar mechanical plotting systems determined firing solutions. 2 fortress observation posts would transmit bearing information to a central mechanical device, and the intersection of mechanical arms set to those bearings indicated the target's location with remarkable precision. All of this got done mechanically, with no electrical components involved. These plotting instruments were constructed to reduced scale, a mechanical model of the actual geography with arms that could be positioned according to received bearing information. Through mechanical geometry, pure physical mathematics, the system calculated firing solutions. This technology is almost entirely forgotten today, but the principle remains sound because mechanical systems can solve complex mathematical problems through the precise arrangement of physical components. Number 7. The detonator that changed everything. Proximity. Fuse. Before proximity fuses, artillery shells and bombs had only 3 detonation methods: direct contact, a timer set at launch, or an altimeter, and all of these had severe limitations. A shell that barely missed its target would not explode. A timer fuse required accurate prediction by the gunner and precise timing by the fuse mechanism, and if either was wrong, the shell exploded harmlessly before or after passing the target. At the start of the Blitz in London, estimates suggested it took somewhere between 20,000 and 100,000 artillery rounds to shoot down a single aircraft. And that's how difficult the targeting problem actually was. Proximity fuses changed everything by detonating when the shell approached within a certain distance of its target, eliminating the need for direct hits or perfect timing. The concept originated in Britain with Samuel Curran, William Butemant, Edward Shire, and Amherst Thompson at the Telecommunications Research Establishment, proposing to use small-range Doppler radar within a fuse. But the critical miniaturization work, creating a fuse that could survive the extreme acceleration of being fired from a cannon and the immense centrifugal force of a spinning artillery shell. That work happened in America. Physicist Merle Tuve and his Section T team at Johns Hopkins Applied Physics Laboratory solved the engineering challenge. The fuse contained 4 or 5 electron tubes, where one tube acted as a transmitter connected to the shell's antenna, continuously emitting radio waves around 180 to 220 megahertz. As the shell approached a target, the transmitted signal reflected back, and the fuse detected this reflected signal. The movement of the shell and target created a Doppler frequency shift, a change in frequency due to relative motion, and this frequency shift was the signal that triggered detonation. To survive the extreme stresses of artillery launch, engineers packed components in wax and oil for stress equalization, replaced conventional electrodes with planar electrodes, and modified miniature hearing aid tubes to withstand up to 20,000 Gs of acceleration and centrifugal forces from shells, spinning at 30,000 RPM. The effectiveness was dramatic. In 1942, a test aboard the USS Cleveland destroyed 3 drone aircraft with just 4 projectiles. And by 1943, when only 25% of naval anti-aircraft ammunition used proximity fuses, those fuses accounted for 51% of the aircraft kills. Production scaled enormously over the war years. Over 22 million proximity fuses were manufactured, and the cost dropped from $732 per fuse in 1942 to $18 in 1945, a 98% reduction through manufacturing efficiency. Over 100 American companies got mobilized for production, and by 1944, a large proportion of America's entire electronics industry was dedicated to making proximity fuse. In the Battle of the Bulge, 200,000 shells with proximity fuses, codenamed POSIT, were deployed in December 1944, and General Dwight D. Eisenhower had personally demanded access to these fuses after initially being denied them. General George S. Patton credited proximity fuses with saving Liege and stated that their use required a complete revision of land warfare tactics. German divisions, confident they were safe from timed artillery fire because bad weather would prevent accurate observation, got caught in the open by proximity-fused shells exploding just above the ground. In the Pacific, proximity fuses increased the effectiveness of 5-inch anti-aircraft artillery, 7-fold against kamikaze attacks, and in Europe they were instrumental in finally neutralizing German V-1 flying bomb attacks on England. The proportion of flying bombs destroyed by coastal gun batteries rose from 17% to 74%, reaching 82% on one exceptional day. Admiral Lewis Strauss summarized it this way: "One of the most original and effective military developments in World War II was the proximity fuse, and while no one invention won the war, the proximity fuse belonged among the very small group of developments, such as radar, upon which victory very largely depended. The government classified it at levels comparable to the atomic bomb because security was so tight that Soviet spy Julius Rosenberg managed to steal a working model only by finding a non-anti-aircraft variant, and the most valuable type remained secure." Number 8. The torpedo that guided itself. Torpedo guidance systems represent one of the oldest mechanical technologies, refined to remarkable precision by World War II. Every torpedo guidance system relied on a gyroscope spinning at enormous speeds, often 15,000 to 20,000 RPM. This spinning mass possessed a remarkable physical property: resistance to changes in its rotational axis. A gyroscope wants to keep spinning in the same direction. This property got exploited brilliantly because the torpedo's gyroscope got aligned along the torpedo's body axis. And as long as that gyroscope maintained its spin and orientation, it provided a mechanical reference point. Connected to this gyroscope was a mechanical linkage system, and if the torpedo began to deviate from its set course, this linkage would detect the deviation and actuate corrective rudder movements, all mechanically, without any electronic components. The Japanese Type 93 Long Lance torpedo, considered by many to be the best torpedo of World War II, used oxygen and kerosene propulsion, a mechanical gyroscope for stability, and carried a large warhead that gave it advantages over contemporary alternatives. American submarine torpedoes used pressure-driven air systems to power the gyroscope spin-up mechanism, and mechanical spring mechanisms controlled by air pressure would unlock the gimbal structures, the rotating mounts, allowing angular correction. Some torpedoes could be set to run in directions different from the tube axis, allowing what got called gyro-angled torpedoes, and the mechanical angle setting capability could offset the initial course by up to 90 degrees. Separate mechanical mechanisms maintained the torpedo at a constant depth, keeping it from passing beneath the target ship. The American Navy encountered significant problems with the torpedo performance, not because the gyroscopic guidance failed, but because the depth-keeping mechanisms sometimes malfunctioned, causing torpedoes to run deeper than set and pass underneath their targets. Eventually corrected, these were design failures rather than fundamental flaws in mechanical gyroscopic guidance. The principle remains elegant because a spinning mechanical device, resistant to directional change, provides reference and control through pure physics. No electricity, no active components, just gyroscopic inertia and mechanical linkages. Number 9. Cipher machines that typed secrets. During World War II, the U.S. Army used a portable mechanical cipher machine called the M209 for encoding and decoding secret military messages in the field. The M209 operated on rotor principles, using a series of rotating mechanical disks to substitute letters in a predictable but changeable pattern, and it was compact enough to carry in the field. It required no electricity and was entirely hand-operated with a crank mechanism and rotor adjustments performed manually. The distinction matters because while the Enigma machine, famous for its role in German communications, appeared similarly mechanical, it actually required electrical power for operation, whereas the M209 was truly mechanical. Rotor substitution cipher performed entirely through manual operation and mechanical rotation. Compared to higher-level cipher systems, the M209 provided adequate field-level security for tactical communications, and its strength lay in its portability and mechanical reliability. It was rugged, could be transported easily, and functioned dependably in field conditions. These mechanical cipher machines represented a practical solution to the constant problem of warfare, keeping communication secure while maintaining enough portability that units in the field could encode and decode messages quickly. Number 10, detonators and fuse. The mechanics of explosion. Before proximity phases revolutionized detonation, armies relied on mechanical fuses that operated through remarkably simple principles. Burning rate fuses used powder trains that burned at calculated rates to achieve predetermined detonation times, and artillery gunners would calculate the expected time of flight for their shell based on distance and firing angle, then set a corresponding time value on the fuse. The powder train, burning at a known rate, would reach the detonator at approximately the correct moment. The problem was that burning rates varied. Manufacturing tolerance created unpredictability, and battlefield conditions, temperature, humidity, altitude, affected how powder burned, resulting in significant variation in actual detonation times. Mechanical clockwork fuse represented a more controlled approach, where internal mechanisms wound like a clock would hold detonators mechanically, and when the preset time expired, the mechanical release would trigger the detonator. Contact fuses were even simpler because a spring-compressed firing pin held back by a mechanical safety would, upon impact, get overcome by compression, driving the firing pin forward into the detonator. Arming wires deployed during free fall or launch would release the safety mechanisms before the bomb or shell reached its target. These mechanical detonation systems represented the state of the art for decades because they were reliable, relatively simple to manufacture, and required no electrical components. The mechanics of explosion got controlled by purely mechanical means. Number 11. Navigating without electronics. Air navigators and ship navigators during World War II relied on mechanical instruments and manual calculation for their survival and success. RAF bomber navigators in World War II used maps, mechanical plotting rulers, compasses, chronometers, and sextants for celestial navigation, and dead reckoning, calculating position based on known heading and airspeed, required only mechanical instruments. Navigators would mark their course on maps using mechanical rulers, calculate distance using dividers and compasses, and verify position using visible landmarks whenever possible. Ship navigators employed chart table plotters, mechanical instruments with rotating brass arms, and transparent rulers for plotting positions and calculating bearings. These devices had no electrical components and functioned through mechanical geometry. Naval plotting tables enabled precise position calculation through mechanical means, where rotating arms got set to receive bearing information from observation posts, and the intersection of these mechanical arms indicated the target's location. Coastal defense batteries used similar mechanical plotting systems. Aviation plotting instruments served similar purposes by providing mechanical tools for position calculation and course plotting, and the mathematics got performed through the arrangement of physical components, gears, rotating discs, and mechanical linkages that physically embodied the geometry of navigation. These systems worked. Navigators planned bombing runs using mechanical instruments. Ships plotted courses. Artillery batteries calculated firing solutions. The mathematics of navigation got encoded in brass and perspex and rotating gears. Number 12. Mechanical weapons and deception. The M2 backpack flamethrower operated through pressurized fuel delivery without electrical components. Pressurized fuel tanks arranged in a backpack configuration fed fuel through a hose to a nozzle assembly, and a manual valve controlled fuel flow through a trigger mechanism. At full force, the weapon expelled 1/2 gallon of fuel per second with an effective range of 65 feet and approximately 7 seconds of burn time. The mechanical principle was straightforward. Pressurized container, control valve, ignition. Designed to be carried and operated by a single soldier, weighing 68 pounds fully loaded, it got deployed in both Pacific and European theaters during World War II, in Korea, and Vietnam. But perhaps the most creative mechanical deception system was the Ghost Army, inflatable decoys deployed by the U.S. Army's 23rd Headquarters Special Troops. These were canvas-covered inflatable tanks, artillery pieces, and vehicles that collapsed flat for transport, then got inflated on site using mechanical pump systems with steel framework supports, maintaining shape and paint and camouflage patterns, providing optical deception. Positioned to resemble authentic military units, these mechanical decoys repeatedly deceived German reconnaissance aircraft and forward observers. German intelligence would report sightings of fortified positions, artillery concentrations, and tank formations that were entirely inflatable. Enemy units would avoid positions that were nothing but rubber and canvas. Dummy aircraft and airfields got constructed with painted runway markings. Fake factory installations got built to draw bombing attention away from real targets, and camouflage netting, supported by mechanical framework, concealed actual military positions. This was psychological warfare through mechanical means, deception engineered in rubber, canvas, and steel. These 12 technologies represent something modern culture has largely forgotten: the possibility of sophisticated, effective military systems requiring no electrical power, acoustic mirrors that listen to the skies, mechanical computers that calculated artillery trajectories, mechanical gyroscopes that guided torpedoes, inflatable decoys that deceived the enemy. Some worked brilliantly, others failed in their intended purpose, but contributed to something greater. The acoustic mirrors failed at detection, yet their methodology contributed to radar success. Some were evolutionary dead ends, like the mechanical cipher machines that got replaced by electronic alternatives. Others, like the proximity fuse, proved so effective they genuinely changed the course of warfare. What matters is the engineering achievement. A 3,000-pound mechanical computer calculating firing solutions. A mechanical analog calculator that performed multiplications through rotating discs and gears. A torpedo that guided itself through gyroscopic inertia and mechanical linkages. A bomb sight that was a mechanical computer in its own right, its wheel and disc calculator continuously solving complex equations through pure physics. We moved past these technologies quickly and embraced electronics, solid-state physics, and eventually digital computing. And we were right to do so because these mechanical systems had limits. But we lost something important: an understanding of how to solve complex problems through pure mechanical means. These forgotten technologies teach an important lesson for anyone interested in engineering, history, or problem solving. Sometimes the most elegant solution isn't the most complex. Sometimes it's rotating discs and mechanical linkages. Sometimes it's the physics of sound reflection or gyroscopic inertia. Sometimes it's human ingenuity applied to mechanical constraints. That's the story of these 12 forgotten World War II technologies. They worked without electricity, and for a moment in history, they changed everything.